Let's find out how accurate this machine really is. We're gonna barbell it.
It's bald bar, you knucklehead!
Oh, come on, why doesn't anybody tell me this stuff? Hello everyone and welcome back to Atman Unlimited. Today we have our first guest. This is Brian, and Brian is from Machine Laser Calibration. And he is nice enough to come in and let us film his work, and he brought in a ball bar. A lot of people have been asking about this video, so we'll get to work, we'll put the ball bar in the machine, and we'll see how accurate the machine really is. Time to put your money where your mouth is. Before we actually put the ball bar in the machine, it's always a good practice to verify the level of the machine and make sure that the bed is not twisted. Now you'll recall that I did a leveling video and showed that the machine does have a little tiny bit of twist in it. We were using a spirit level in that video, and that level had an accuracy of 10 arc seconds per division. Now Brian was also nice enough to bring in an electronic level, and this level is really accurate. Each hash mark is 1 arc second. So this level is extremely sensitive. And we did confirm that there was about 5 arc seconds of twist in the bed. And we played with the feet a little bit more to try to get it a little bit better. And what we ended up with was about 3 arc seconds of twist in it, which is extremely respectable for a machine like this. So just wanted to show you the leveling that we did check before we put the ball bar in. And then now we'll put the ball bar in. So we're installing the ball bar in the machine. There's a base that just magnetics down onto the table and has a metal ball. And then there's a receiver that goes in the spindle that has a cup. And then the ball bar has a cup on one side to go on the ball, and then a ball on the other side. Now inside the cups are magnets, and then there's these little copper bronze fingers so that there's kind of like a bearing surface, so it's very accurate and it doesn't move around. Now with the ball bar comes a calibration standard, and that's what Brian was doing. It's basically just a board with balls on it at set distances. So you snap the ball bar on those balls, and then you tell the computer, okay, calibrate it, and it knows what the distance is between those two balls. So after you have it calibrated, you snap it in the machine, and then Brian's measuring the temperature of the machine, and then the software will compensate back to a reference temperature for you, so you have to tell it what the temperature of the machine is, and then it knows how much temperature compensation to apply. So what is a ball bar actually, and how does this thing work? How do you get so much information out of such a simple device that just does a sweep of a circle? Okay, so the ball bar itself is actually, at face value, a pretty simple device. All that bar does is measure the distance between the spindle and that point on the table, but it can measure it very, very accurately. That's all it does. It's just a displacement, positional displacement transducer. Okay? Now, what the computer software does, and that's where the magic happens, is it knows what feed rate you set the machine to, and then when it starts its sweep, the spindle will move in to the ball bar a little bit, and that's its trigger to start. And then as soon as you move in, it starts its circle. After it's done with the circle, the spindle will move back out, and that triggers the computer to stop. So then the computer can time exactly how long it took to make that circle, and it knows what feed rate, so it can tell you how accurate your feed rate is. And then also, by knowing where it's starting and stopping and what time it's starting and stopping, that's how it synchronizes the positional measurements with the rotation of the circle. So it knows I'm at 12 o'clock, or I'm at 6 o'clock. So it uses it by time. So there's no encoders or angular sensors in this thing. It is strictly just a linear displacement sensor with a lot of really smart, good software behind it. So then what can we measure from the ball bar? We can get squareness, we can get straightness, we can get backlash, we can get servo drive tuning match. So there's all kinds of parameters that you can get just by doing this simple sweep. And this is why this tool is so valuable, because it can give you the general health of a machine very quickly and very accurately. So it's much faster than having to set up the laser and do a whole laser calibration if there's nothing wrong with the machine. So this is where Brian typically starts. He'll run a ball bar on a machine, and if the ball bar comes out good, typically they don't need to use the laser unless the customer really wants, a true laser calibration. So this sweep is in X and Y, so we're going to check the XY plane of the machine. And then you run one sweep first, and then you tweak in your work offsets so that you really know where the zero of the ball bar is, and then you'll run another sweep just to collect the data. So let's look at the software on the computer while we're doing a sweep, and I'll show you the display that it displays in real time. Here's the real-time display from the ball bar software. Right now the software is waiting for the infeed to trigger it to start its acquisition. So I've got the real-time display on the computer, and then you've got a picture of what's actually happening in the machine. So you can see we did the infeed, and then it immediately started the circle. Now what this plot is this plot is an error plot. So the dotted line, the circular dotted line, is perfect. If you're over the dotted line on the outside of it, you're too big. If you're inside the dotted line, you're too small. Now Brian says that if the plot looks really bad, it actually means your machine's really good, because this plot auto scales. And right now the scale of each one of those little hash marks is 1/10,000th of an inch. So we're actually pretty good here. Now just by looking at this plot and watching it run, you can already ascertain some information from it. One of them being is that Y is not backlash comped as good as it could be. So you can see in the Y, you've got these stair steps as Y comes to a stop and then starts again in the opposite direction. So that was the one adjustment that we did have to make on the machine, is we tweaked in the Y backlash. And that was pretty much the only adjustment that we had to make. Everything else was pretty good. The X backlash was good. The Z backlash was real good because I just replaced the Z ball screw. The squareness of this machine was spectacular. It measured out the squareness between X and Y at 0.1 arc seconds. So it's really square. So once we do the counterclockwise rotation, then it comes back and does the clockwise rotation, and then the algorithms will take over and combine all the data from those two plots to give you a whole bunch of detailed information, and that will come up on the screen next after it completes the sweep. You can see how it's using the feed rate to synchronize, and it's perfectly synchronized between what you see on the screen and the angular position that it's at in the actual real sweep. So now the sweep is complete. The software will process the data that it just collected, and it will bring you a detailed analysis of the data. So there's the plots for clockwise and counterclockwise. And then it's kind of hard to read, but it gives you a breakdown of what each error is contributing to your overall positional tolerance. So when we first did this run, we had a positional tolerance of about 1.3 thousandths. So not as good as we not as good as we could be. The circularity of the actual circle was pretty good. It was under a thou. And a big contributor, if you can read it, it's 16% of our error comes from the Y backlash. So just by changing the Y backlash comp, we were able to get the overall total positional tolerance down to under a thou. So the next big hitter after the backlash was servo drive matching, and we chose not to mess with that because really under a thou of positional accuracy is really good for this machine, and it's an analog machine, so adjusting those servo drives is a pretty tricky proposition. You may never get it as good as it is now just because of the way the potentiometers are. So now let's look at making a sweep in the XZ and the YZ planes. So here we just set up the ball bar to do a YZ sweep rather than XY. So the offsets are all the same, just the program is different, and it actually starts it a little bit below the plane that we used on XY so that you don't get any start and stop anomalies in the actual data. So we're doing a 180-degree sweep here, and it's going to go again clockwise, counterclockwise. And Brian starts with a 180-degree sweep just because you don't have to change the setup at all. And then you can look at what the positional accuracy is based on that 180-degree sweep. And if it's good, you can stop there. If it's bad, what Brian will do is he'll redo the setup so that the magnetic base that's on the table now facing up will face sideways, and then there's a different attachment for the spindle so that he can do a full 360-degree sweep in the YZ or XZ planes. And then by doing a full 360-degree sweep, that's how you can get the full detailed information that we saw in the XY sweeps of squareness and all of that. So then let's take a look at the report and see what information is actually given from the report and given to the customer. So here we have the report that the customer is provided when they get the service done on their machine. And the report contains the error plot that we saw in the real-time display. And then we also have this information over here of how much each item is contributing to your overall positional tolerance. So this number right here is the big number. So this number is telling you that within the 12-inch circle that we ran, we will be able to place a location within roughly 1/1000th of an inch, anywhere within that 12-inch circle. So that's pretty darn good. Now if we look at the breakdown of where all the error is coming from, if you look right here, this is backlash. So you can very easily see backlash here. So the Y screw didn't have its backlash comp as good as it could. So this is the very first run that we did before we made some adjustments. Now if you notice, the backlash comp on the negative side of Y is really bad, but the backlash comp on the positive side of Y isn't as bad. And the X backlash comp is pretty decent. So what we were able to do is we were able to compensate just this negative Y backlash comp by a couple more tenths, and then dial this one, and I think we changed this one 1/10 to really get this circle to be much more accurate and much more round. Now, I don't want to go into the deep dive in how to interpret all this information, but by looking at how the circles are going, see how this side's under and this side's over, and then how the shapes are, that is how you ascertain squareness, servo drive mismatch, gain mismatch of the ball screw, is an inch really an inch, but the software does it all for you. So you can see here 19% of our error is associated to servo mismatch. So the gain of the servo drives are slightly different, so they're running at slightly different rates. We've got 17% in reversal spikes on X. So one of my comments in my other videos was backlash comp is good, but if your screws get really bad and you need a lot of backlash comp, it will start affecting other things. And that's where these reversal spikes are coming from. It's the backlash comp when the screw reverses direction, kind of bumping up against the screw, and it makes a little disturbance in the positional plot. Then we had 17% of Y backlash, We chose to fix this one because it's really easy to fix. We just changed a register in the machine. We had a little bit of scale mismatch between X and Y. And then Y had a little tiny bit of straightness. But if you look at this, it's like almost 3/10 of straightness. So it wobbles a little tiny bit. So Y, the linear rails are the original linear rails, but I did straighten them. Y was much worse than this before I straightened them using the granite square that you saw in previous videos. So then this was the first run. Let's take a look at the second run. So the second run is all the way down to the bottom. So then this is the second run. Now notice our positional accuracy is slightly better. We went down to 9.7 tenths from 9.8 tenths. And if you notice here, see how much this plot is, this deviation? We can compare it, and you can see how it's much less here. Okay, so we were able to dial in the backlash pretty good, but notice, see these spikes that you've got here? That's the backlash comp working. So while we were able to reduce the backlash, we increased the reversal spikes slightly. Not a lot, but slightly. It's better than, the reversal spikes are better than having the backlash in there. So you can get a detailed report, and this is all of the numbers that the software will throw at you. It will tell you what the current backlash is. So we still had about 1/10 of backlash in X. Y, we had almost no backlash. Your reversal spikes. So on one side of Y we had almost no reversal spike, and on the other side we had 3/10 of a reversal spike. So again, that's the backlash comp kind of playing games with the ball screw. Servo mismatch. Squareness was a big one. This one was, I was really proud of that one because I squared this machine just using a granite square and a dial indicator. So keep that in mind. While these tools make life a lot easier and you can get a lot more accurate readings, using a granite square and a dial indicator can still get the job done. These tools are very expensive. The ball bars and lasers are very expensive, and they take a lot more expertise to use them. But your home shop person, if you have a granite square and a dial indicator, you can get your machine dialed in pretty good. So here's our straightness plots. So Y had about 2.3 tenths, X was 1.3, so the X has new rails in it. Scaling mismatch, so Y, the scaling on Y, the Y screw is a little bit low, but this equates to like 2/10,000ths of an inch over 10 inches, so it's not enough for me to want to play with it. And then we also had some cyclic errors, so if we go back and look at the plot, see this jaggedness in here? Okay, that's the servo loop kind of jittering around a little bit. And this could be contributed from a lot of things. It might be that the ball screw's got a little rumble in it. It could be misalignment of the motor relative to the axis of the screw, so the motor coupler might be slopping around a little bit. So again, that's something that you could investigate and get better. It's all of how much time you want to spend to adjust this machine. Again, this is more than accurate than what I need and what a lot of my customers are requesting. So we're good. So you can see you can gain a lot of extremely detailed information from just a simple ball bar test. Now also we got the plots for ZX, so this was our 180-degree plot. And again, all of our values are under 1,000 and in the same range of positional accuracy. Now with the Z, we could probably get the Z in quite a bit better by just adjusting the servo gain. So if you notice here, this side of the plot, excuse me, looks real good, and this side of the plot kind of mushrooms out and then comes down. This is what's called servo drive balance. So while the gain of the drive isn't bad, it's not running at the exact same rate in extend versus retract. So we could probably get this a little bit better, but again, we're well under 1,000, so not too big of a deal. And then here is YZ. So again, YZ has a very similar plot. and that's how you can tell comparing XZ to YZ that the Z servo axis drive could probably use a little bit of attention and adjustment. Okay, so I've got one more plot I'd like to show you. So all of these rough tests were run at 40 inches a minute, and 40 inches a minute is nice because they don't take forever. We did do one plot at 20 inches a minute. So you say, okay, let's look at the final XY plot. So we've got 9.7 tenths of positional error. Okay, and you can see that, you know, we mushroom away from our ideal plot quite a bit here. Let's look at a 20 inch per minute plot. So now with a 20 inch per minute plot, you can see everything tightens up. And that's because of that servo tuning mismatch. So as you go slower, the servo tuning becomes less critical. Okay? And everything kind of calms down a little bit. So if you need to, you know, interpolate a hole and try to hold a lot tighter accuracy, you know, slowing your feed rates down will generate a little bit less error, and you'll be able to make a little bit better part. So we went from 9.7 ten-thousandths of an inch of positional tolerance down to 7.5. So, you know, about a 20% decrease in error. Again, not bad. So that's the report, and we did pretty good. So, you know, all of our previous videos that we made for the machine alignment series, you know, here's the proof that you can do it with just simple, you know, manual instruments. The biggest expense item that you saw in those videos was that ladder gauge. That ladder gauge is pretty expensive to use, so you know, you need a way to calibrate your ball screw scaling. But again, the ball screw scaling is very, very low. I mean, you're talking about a couple of tenths here and there for most ball screws. The ball screws today are manufactured very accurate. So there we go, there's our ball bar calibration. You can see how by using the ball bar you can quickly survey all axes of a machine and get some really good data. So you saw the videos from the manual calibration that we did using a square, an indicator, and then the ladder gauge. The ball bar is just another layer up of accuracy in how we can measure these machines. So this machine, we were able to hold a positional tolerance of about 1/1000th of an inch. So that's pretty darn good. I'm quite happy with that. So thank you to Brian for coming in and helping us out with the ball bar, and we'll see you on the next video.
You're welcome, Tim, and he did an outstanding job with us.